Well, now that we've completely finished our section on functions, we're going to take a look at relations. Now, is the fact a fact that every function is a relation, but not every relation is a function? Basically, every single set of ordered pairs is a relation. So let's take a graphs. These are graphs of, I was going to say of functions that we know, but only the left one on the left is a function. Y equals x squared. And this one would be x equals y squared. It's not a function. Do you remember the rule, the vertical line test? This doesn't pass the vertical line test. In fact, if we went out 1, 2, 3, 4, if x were 4, y has two values. It has +2 and -2. My graph's not very good, but those 2 points are supposed to be 4, 2 and 4, -2. So both of these are relations. In fact, anything you draw into the plane, no matter how you draw it, it can cross, it can loop around, it can do whatever you want. That's a relation. Functions are the ones that are very specific. For every first value, for every ordered pair, the x value, you can only have one specific y value for it. Okay, let's get a little more formal definition. A and B can be any sets. A subset R of the Cartesian product. Remember what this is, A cross B? That's a set of all ordered pairs where the first element comes from A and the second element comes from B. It's a relation, period. Any subset of A cross B, whatever those sets are, it could be reals and reals, which would be like all of R2, the entire xy plane. Any subset of that is a relation. If R, a relation, is equal to A prime cross B prime, and I didn't exactly say what that meant, but A prime would be a subset of A, B prime would be a subset of B. If that's the relation, then A prime is the domain. I didn't have room to write it out, so domain of R, and B prime is the range of R. The left one is the domain, the right one is the range. I think you're used to that terminology. And then next, for a relation R, if this ordered pair happens to be in the relation, we just say that A is related to B. So A is related to B. All right, let's just take a look at several fairly simple examples. Well, the first one, A cross B. One way of defining a relation, these two are the extreme cases. One of them is the empty set. Since a relation is a set of order, it's a set, it can be the empty set. So this would be the relation that has no elements in it. And then another relation would be take the entire set A and the entire set B, and that gives you a relation. The reason being is that the empty set and A cross B are both subsets of A cross B. A cross B is all of the ordered pairs where the first element comes from A and the second comes from B. So that big set, the empty set is a subset of it. The empty set is a subset of every set. And then the entire thing is also, it's a subset of itself. So you could say this is the smallest relation from A to B, and this is the largest relation from A to B. Second one, A is the set 0, 1, B is the set 2, 3, 4. One relation, I just made it up, was I took 0 and 2 for one ordered pair. I took 1 and 4 for another ordered pair. I just called it R1 for relation 1. I just made that up. It's a relation. It's a relation with two elements, two ordered pairs. So how many relations would there be from A to B? Well, how many subsets are there? How many elements are in A cross B? A cross B. Remember that those vertical bars, the absolute value means how many elements are in that set, in this set of ordered pairs. Well, it turns out it's just that, right? You have 2 here, you have 3 there, you can make 6. You can map this 0 to either 1, 2, or 3, this one to 1, 2, 3. I counted up 1, 2, 3 twice, and that gives you 6. So for this example, it's 6. That's not the answer to the question, though. That's how many elements are in A cross B. How many relations exist from A to B? Well, a relation is going to be a subset of A cross B. Do you remember how many elements a subset of a set has? Well, if A cross B has 6 elements, then the number of subsets of A cross B would be 2 to the 6th. 2, 4, 8, 16, 32, 64. That's the answer to the question. If you wanted to, you could write them all out. It might take you 15 or 20 minutes, but... Okay, next example. For two integers, A and B, let R be this relation. It's a set of ordered pairs where A and B, remember, are integers, where B is equal to NA for some n in the integers with absolute value being greater than 1. So if n is an integer with absolute value greater than 1, it means it can be any integer except for 0, 1, and -1. That's a relation. And what would be one element in it? Let's see. 12 is equal to 3 times 4. I'm lining those up like that. That means 12 is equal, so 12 could be A. Oh, I'm sorry, that would be B. B, and then A would be this. So 412 would be one element of that. So I could say 412 is an element of R, but 4 is not an element of R. Because 4, when B is 4, it is not, there's no integer n you could multiply 4 by, no integer that's got an absolute value greater than 1 that you could multiply it by. That would give you 4. Okay, the next one, the set of all A and B where A is less than B. And if we don't really specify where the sets are coming from, just assume it's all reals. So we will assume that A and B are chosen from the real numbers. That's a relation on R. And I could say that pi, comma, 4, is that or is that not? It is an element of R. Why? Because they're both real numbers, and the left one, the A, is less than B. I could pick pi, comma, pi, and they're equal to each other, so it is not the case that pi is less than pi. That is not an element of R. Number 5. Let's see, number 5 is a relation. Number 5 says, and this is a weird one, because in the ordered pairs, the first element and the second element are both sets. So these are both sets. This set, comma, this set, such that A is a subset of B, which is a subset of X. So X is some non-empty set out there. And what does this mean? The power set of x. Do you remember what the power set is? The power set of x is all of the possible subsets of x. For example, A is a subset of x, B is a subset of x. We also know that A is a subset of B, so think of it as maybe being maybe a smaller set than B. So depending on, I'm not going to do any examples because I didn't define what x happens to be, what the set x happens to be. I guess I need to, oh no, I already have that right here. So this is a relation on the power set of x. A and B are both in the power set because they're subsets of x. And as long as, let's say x were the numbers from 1 to 10. One example would be, the set A is 1, 2, 3, and the set B is 1, 2, 3, 4. A would be a subset of B. They're both subsets of x. So that is a relation on the power set of x. The last one is also another obscure one. This is my capital F. Let's let this be the set of all S's, capital S, the subset of integers. So S is a subset of the integers such that it's finite. So for example, in F, you could have -3, -5, -10, and 150. That's a finite subset of the integers, therefore it's in F. So R is a relation where A and B are sets taken from the integers, where they are of equal size. The number of elements of A is equal to the number of elements in B. So, for example, the set 1, 2 and the set 9, 10. They have the same number of elements, so that set, that ordered pair, would be in the relation. If you took 1, 2, 3 and 3, 4, 5, 6, then they would not be in the relation. So another way of saying it is any two finite sets that have the same number of elements are related to each other.